Hi, in this video, we'll learn about the fast Fourier transform. The fast Fourier transform is a more efficient way to do the discrete Fourier transform. The fast Fourier transform takes n log n operations versus n square operations as compared to the discrete Fourier transform. Now, to get to the fast Fourier transform, let's take an example of the four-dimensional Fourier transform, and let's see if we can find some symmetries in it. So let me write the matrix of F4. So this is 1, 1, 1, 1, the first column, and 1 minus I minus 1I. And then this is 1 minus 1, 1 minus 1, and this is 1 I minus 1 minus I. So this is the 4 cross 4 matrix of the four-dimensional Fourier transform. Now, the first step to do is to exchange the columns. So we'll get the even column. So if I say this is column number 0, this is 1, this is 2, and this is 3. So we'll exchange the 1 and 2 such that we can get the even columns too. So we'll do a permutation of the columns. So even, odd. So this will give us a new matrix, which is 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1 minus I minus 1 I, and 1 I minus 1 minus I. Okay. So once we have done that, observe that there are some symmetries over here. So if I divide this 4 cross 4 matrix into sub-matrices of blocks 2 cross 2. So if I do this division over here, right, what do we get? We notice this is just the two-dimensional Fourier transform. So this is F2. This as well is F2. So I can write this as F2, F2, and I can write this matrix, the 2 cross 2 matrix, which is this one. I can write it as 1, 0, 0 minus I multiplied by 1, 1, 1 minus 1. And similarly, I can write this block as minus 1, 0, 0 I multiplied by 1, 1, 1, 1 minus 1. And then again, notice that this is just the two-dimensional Fourier transform. So this F4, I can then write it as F2 D2 F2 F2 D2 minus D2 F2, where D2 is a diagonal matrix. Okay, so D2 is this diagonal matrix 1, 0, 0 minus I. Right? So what have we achieved? So we have written basically a larger matrix as some block matrices which are of smaller dimension. But then we have also written them in such a way that there are more now zeros over here. So notice D2 has is a diagonal matrix. And so the idea is to successively do that. So if I have, so n is equal to 2 to the power r, then the idea is to successively decompose the Fourier matrix, the large Fourier matrix, into smaller Fourier matrices. And we do that for log n steps, right? So we do that, and each step, what will happen at each step is that the number of multiplications at each step will reduce, resulting in this n log n efficiency. So we will get to that particular point a little later, but let's first prove that this general formula exists. So what we want to show that Fn is equal to Fn over 2 Fn over 2 dn over 2 n over 2 minus dn over 2 Fn over 2, where dn over 2 is a diagonal matrix and Fn over 2 is the n over 2 dimensional Fourier transform. Right, so let's state the theorem. So the theorem is, let's state and prove the theorem also. Theorem is let Fn be the n-dimensional Fourier transform then Fn is equal to Fn over to these blocks. You can decomposed as these blocks, Fn over 2 minus d n over 2 Fn over 2. And of course, we have to do the interchange of the rows and columns, so that we will define by P of n. This is a permutation matrix where Pn is equal to E0, E2, En, E1, E3, E5, and so on, and En minus 1. We are assuming n is some power of 2. So I'm sorry, this should be Pn transpose. Right, so we're going to prove this theorem. Essentially, this Pn just interchanges, I'm sorry, this is Pn. Essentially, this Pn just interchanges or exchanges the columns in such a way that the even columns are together and the odd columns are. So the proof is the following. Well, the key idea of the proof here is that if I have the nth root, the conjugate of the nth root of unity. So this is the conjugate, complex conjugate of the nth root of unity. Then this square, if I take the square of this, then this is the n over 2 root of unity. Okay, so this is the key idea of the proof. Now, if I just draw a picture over here, if I draw the picture, let me draw a circle. This is the unit complex circle, right? So if I have, sorry, this was not what I wanted. Okay, so this is, draw a circle a little bigger. Okay, so if I have, let's say if I have the 6th root of unity, then it will be right over here. So this is drawing the 6th roots of unity. So this is omega 6, omega 6. So this is 1 and omega 6 square, omega. So this will be angle 60 degree. This will be 120 degrees. And then 180 will be over here. So sorry, this will be omega 6 cube. Then this is omega 6 to the power 4. and this is omega 6 to the power 5. So I have drawn the 6 roots of unity. Now, if I draw the third roots of unity, then the third root of unity, omega 6 square is equal to omega 3, and omega 6 to the power 4 is equal to omega 3 square, right? So the third roots of unity are the squares of the sixth root of unity. So this is the key idea of the proof. All right. So let's first assume that if I take Fn and apply this Pn on it, okay, which is the permutation, right? So I have this. This is the same as Fn applied to Pn transpose is equal to this matrix, right? So if I apply Fn to Pn transpose, I will essentially exchange the rows and the columns in such a way that the even columns come together. So let's assume that this can be written as some 4 block matrices n over 2 cross n over 2, b n over 2 cross n over 2, c n over 2 cross n over 2, and d. No, let's not write d because we need that alphabet for something else. So g n over 2 cross n over 2, right? So let's assume that once we have exchanged the columns, we can write the Fourier matrix as this block matrix. Now, what we know is that Fn, the jkth element of Fn, is eta to the jk. This we know from before. And as I mentioned that if I take n over 2, right, the jkth element of Fn over 2, then this is the square of the jkth element of Fn. So this is 2jk. And another thing to notice is that what we'll need is that if I take eta to the n over 2, right? So this is the nth root of unity. If I raise it to the n over second power, then this is minus 1. Okay, as you can see over here in this picture is that if I take omega 6 to the power 3, this is actually is minus 1, right? So that's the 3 things we'll need. Now, let's look at a n over 2 cross n over 2, right? So what we have done after this step, this is essentially equal to F0 star F. So I'm writing the columns F2, F star 0, F star 2, F star 4. So I've brought all the even columns together. 1, F star 3, and so on, F star n minus 1, right? So what this is going to be is if I take the jkth element of this, then this is going to be the jkth element of Fn. But now this is, the columns are all even. So this is going to be j n over 2, right? Jk. So this is going to be, sorry, this is Fn and j comma 2k, right? Because we have exchanged the columns. So this is going to be eta to the 2jk, which, as I said before, this is going to be Fn over 2 jk. Okay, so this part we have just shown. After exchanging the columns, so the entries of a n over 2 will be fn of j comma 2k, because we have exchanged the columns and we have got all the even columns together. And since the squares of the uh, nth root of unity is equal to the n over 2th root of unity, we'll get this thing. Now let's look at b n over 2. jk, this will be fn of j comma 2k plus 1, because these are the odd columns. So this will be eta to the j times 2k plus 1, which will be equal to eta to the 2jk, but there will also be eta to the j in front. So this is going to be eta to the j fn over 2 jk. Now let's go to this matrix C. C n over 2 cross n over 2. The jkth element of this matrix will be fn, but now this will be n over 2 plus j comma 2k, right? Because we are going from the n over 2 plus 1th column to the nth column, right? As we progress from this point, so n over 2th column, I'm numbering, remember that I'm numbering the columns from 0 to n minus 1, right? So this will be, again, this will be eta to the n over 2 plus j into 2k, which will be equal to eta to the n into eta to the 2jk, but eta to the 1 n is 1, right? Because it's the nth root of unity, and this is just fn over 2 jk. Okay, so we have shown that also. And then finally d of n over 2 cross d of cross n over 2, not d but g rather. So this is g n over 2 cross n over 2 of j k will be, now this will be fn of n over 2 plus j comma 2k plus 1. These are the odd columns. So this will be eta to the n over 2 plus j into 2k plus 1, which will be to the n. So this will be into eta to the n over 2 into eta to the 2jk into eta to the j. This is 1. This is eta to the n over 2 is equal to minus 1. So this will be minus eta to the j into eta to the 2jk, which is equal to minus eta to the j of fn over 2 jk, right? So therefore we have got a n over 2, b n over 2, c n over 2, and g n over 2, these sub matrices, n over 2 cross n over 2 dimension matrices in terms of the Fourier matrices, except that n over 2 dimensional Fourier matrices, except that this each element is multiplied by e to the j over here. The jth element, jkth element is multiplied by e to the j. Similarly, the jkth element of g of n over 2 is multiplied by e to the minus j. So therefore, we have just proved this. So fn is equal to fn over 2 dn over 2 fn over 2 fn over 2 minus dn over 2 fn over 2, where dn over 2 is equal to 1 epsilon, the eta, and then eta to the n over 2 minus 1. This will be a diagonal matrix, right? And this, of course, this has to be multiplied by Pn. Okay, where Pn transpose is this permutation matrix. I think this should be Pn transpose here, right? So that's it. So we have proved that a Fourier matrix can be decomposed, n-dimensional Fourier matrix can be decomposed as n over 2-dimensional Fourier submatrices, and there is also a small diagonal matrix that comes along. Okay, so this is what we have proved. All right, thank you.